from the Rudiger Boskovic Institute to give us a talk about low energy accelerators and their applications.
Okay, good morning, everybody. So I'll try to share my screen first to find the lecture. Is it this one? Well, just to introduce myself, I'm Milko Jaksic from the Ruđer Bošković Institute, which is the largest institute for natural sciences in Croatia, and it consists of many departments and about 25% devoted to physics. And I'm within the experimental physics department, which has mostly facilities related to work within the country, within the institute, but also we are connected to CERN and astrophysics large-scale facilities. So, oops, sorry, I have to, yeah. So my outline of the talk will be, I will just tell you a little bit about electrostatic accelerators, something about the ion beam analysis, which is one of my main applications of such facilities. And I'll try to refer also to some topics that are important for the topic of this masterclass, and something about the staff, users, and funding. And probably you saw these images of the break peak and the distribution of the advantages of the carbon therapy and why we are here. And give here is just at this end of the trajectory of the carbon ions, for instance, in body or in water here, because our range of energies are far below hundreds of MeV per nucleon or what they are used for hadron therapy. The maximum energy we have is about 10 or 20 MeVs only. So we cover only the last path of these carbon ions going through the body. So I'll first start about the accelerators. These are electrostatic accelerators, different than those that were referred by Marius. And a little bit about the ion beam interactions, the nature of the interaction of ion beam material. So these are two accelerators we have in Zagreb. This one is pretty old, 6 megavolts, moved from Houston, Texas about 30 years ago. And it's based on the tandem principles and electrostatics. So in the center of the accelerator within this tank, there is a high voltage, positive high voltage. Therefore, if we want to accelerate ions, we have to produce them as a negative. So negative ion source is a typically sputtering ion source, which is very convenient as it can produce almost any negative ion. The currents are much lower at the levels of few microamps, but then these negative ions are directed to the accelerated tube. They are attracted by high voltage potential. Within the tube here in the stripper channel, there is a conversion from negative to positive ions. Then positive ions are accelerated again. So this is the tandem principle. And then we have analyzing magnet and directed into the chamber. So the layout of the laboratory, as it is now in Zagreb, these are these two accelerators, larger one and smaller one, and there is many different beam lines. So from each of the accelerator, you can deliver the beam to any of almost any of the chambers, and even we have some two chambers where simultaneously we can put two beams inside, which is pretty good advantage of our system. And so we can then use different techniques. Each of these end stations have some different capability, which I will try to briefly explain in further moments. So this is just a picture of the experimental area. You can see these tubes coming out from the accelerator room, and each of these beam lines have certain capability or certain application. So just to show you what is going on with the ions when they are coming into the material. So you can see the trajectory of individual ions. Let's say this is about this carbon ion of, let's say, something about 3 MeV. So these red dots are ionization events. And you can see that each ion is actually traveling with pretty straight line. And then at the end of the range, there are some more scattering. The green areas are actually scattering with atomic nuclei. And these are two main important, the most frequent processes. There are also nuclear reactions, but they are much, much less frequent than the other two. So when you do many of such ions, you can see that they produce a lot of different ionizations. And most of these processes, which I mentioned, can be used for ion beam analysis, so to analyze material. However, also because of these huge scatterings with atomic nuclei, these techniques, the ions can be used also for materials modification through the damage or implantation. So if we, for instance, put this beam, okay, this is proton beam of 2 MeV into the air, you can see exactly the same shape as one can make a simulation. So this is the beam that fluoresces, that makes ionization of the air, actually nitrogen molecules that then emit blue light. So you can see that the shape of the beam has this end of the range kind of maximum, which is the Bragg peak actually, and that which is used for the hadron therapy also. So let me switch to now some of the applications that we are doing here. I will refer only to ion beam analysis, or there is a lot of ion beam modification of materials. So the basics of the ion beam analysis, that we have to understand the nature of the physical process. So, in most of the cases, this is very, very, very exact, because we know almost everything about the scattering, do it from the Rutherford times, Rutherford formula, or ionization can be modeled very well. We can detect very well the products with 100% efficiency in most of the cases, and by using these two prerequisite, we can really make proper elemental analysis of the target. So when we look at some sample and actually atom, so you have these, let's say, ionization, for instance, the beam will eject electron out of the shell, and then subsequent de-excitation will follow the X-ray emission. Also, the similar thing happens with the scattering, which can be either in a front or a back angle, or nuclear reactions that are also possible. So when we look at the ionization itself, so as I said, we have to eject some of the electrons from the inner shell, and then electrons from the outer shells will go into the empty space and subsequently emit X-rays, which will be completely dependent on the atom, on the atom where it comes from. So by the proper detection, we have a very simple chamber built in our lab with two X-ray detectors here and the target, which are some different unknown sample. You can detect, you can observe a spectrum of different elements, and each of these peaks refers to one of the elements. So these are X-rays of the keV region from, let's say, 1 keV to maybe 20 keV. This is an example of our particular matter filter. So this is for air pollution monitoring. Another example is that we could put the beam into the air. And here is one picture of the Roman silverware found recently in Vinkovci area in Croatia. And then by moving this plate over the beam, by kind of scanning. Each of these X-ray lines can be well sorted into the images, and actually then we can find the composition of each of these parts of the object, and we can determine the technology how some object has been produced a long time ago. The other possibility, which is quite novel here in the lab, is mass spectrometry. So when the very heavy ion beam, like iodine of 20 MeV, let's say, enters the target, from the very, very surface, this is almost first nanometer or first few angstroms, the molecules are emitted from the surface of the sample. And then if you analyze in some way the mass of these molecules, which we do with the mass spectrometer. So this is a time of flight mass spectrometer, where we measure the time between the emission and the detection, which is done in this spectrometer. You can get a mass spectrum. This is extremely sensitive technique, and there are only 3 or 4 such devices in the world, and it's really novel. So we are pretty proud on that, and we expect that there will be many different applications of this technique. So very conventional technique based on elastic scattering is Rutherford backscattering spectrometry. So there is scattering of typically helium ions on the target of on the nuclei of the target. The same chamber can be used as in PIXE, and you have very simple kinematics. You know everything, you know probability, because these are Rutherford scatterings, and you can calculate, actually, you can measure the energy of the scattered ion. This is one simple, also cultural heritage example, where if we have analyzed very old ancient metal threads which were made of silver and coated by gold. And there were 2 different technologies with very thin gold layer. So this is the top layer because gold is heavier than silver. So you can distinguish by measuring energy gold from silver. Also, you can find the depth profile. So this peak here indicates that we have very thin layer of gold at the silver. In addition, in this sample, the gold is actually diffused into the silver, so the technologies are 2 completely different. The other techniques based on the scattering is detecting of recoils. So the beam comes from the here in this example. If you look at the right figure, so there is a beam coming from the accelerator to the chamber, and then we have a low grazing angle irradiation of the sample, and then we have a detection system based on time of flight spectrometer, where we measure at the end energy and time of flight. And then if you display detections of both of the detectors in a way of energy towards time of flight, you can separate many different ions from hydrogen to very heavy. So almost every element can be resolved. This is one example of multi-layered sample with very thin layers of several tens of nanometers. So this is extremely useful for nanotechnological applications. And then finally, nuclear reactions are ideal for the analysis of light elements, let's say lithium, boron, beryllium, most typically, for instance, lithium for batteries, boron for some doping and so on. This is example of analysis of boron by proton beam. So the proton beam was 0.9 protons to 0.9 MeV protons. And as a Q value of this reaction pretty high, we can separate emitted particles from the Rutherford backscattering spectrum. And in this case, that was done with microbeams, so you can even make some images of these very light elements. Light elements are basically in chemistry very difficult to detect. Like hydrogen is extremely different, but these nuclear techniques can be used very well. And then there is also detection of gamma rays as a product for nuclear reactions. There are a list of many different reactions, and ion beam analysis can be adjusted to provide you good sensitivity for one particular isotope that analytical techniques use. And as you can assume that such existing of such techniques is very valuable for collaboration with different scientists, for not just physicists, but chemists or cultural heritage or environmental scientists and so on. Next beam line that we have is so-called nuclear microprobe, where the beams are focused. Again, what Mario was explaining by triplet, because you can actually, with a single quadrupole, you cannot focus the beam in one dimension. You can focus the beam only in one dimension, so you need at least doublet, but triplet is much better in our case. And then by focusing the beam and scanning over the surface of the sample, you can produce this kind of images of the elemental distribution using only pixel detector. So this is extremely useful technique, and most of the pixel, what we do is we are doing with microbeams. Now I'll switch to some of the possible applications that we do that are relevant to hadron therapy at our facility. And as I said at the beginning, if we zoom in into the end of the range of carbon beam of hundreds of MeV. So if we use, for instance, 10 MeV carbon, then we can distinguish the two peaks. The peak in nuclear stopping actually is creation of damage in material. Very interesting for some of the applications. So we'll have at the end of the range increased number of vacancies in the crystal lattice, for instance. And then you have the peak from the ionization. This is break peak, which is kind of distributed over the whole range. So this is a very interesting feature. And this is, you remember from the beginning, distribution of these red and green events, let's say, how the ions are going through the material. So what we do with these low energy ions, we have two projects. One is to calibrate and to study the microdosimeters, which is a very important tool for the hadron therapy, but also not for hadron therapy, for others application. And we also do irradiation of living cancer cells together with biomedical colleagues from our institute. So this is one example how you can actually test the beams that we have or are used in hadron therapy to see the study of effects on the cancer cells. So one of the advantages we have is that we have also diamond membrane detectors. So these detectors serve as a window between the vacuum and air, and then can give us a signal when each of the ion goes to the membrane. So these diamond membranes are positioned just at the exit of the tube, just before the container that in which one you put the cells to be irradiated, so that when ion goes through the membrane, they come directly to the cells. So this is one very good possibility of using these low energy accelerators. This is just one example of the cells we have been irradiated. These are some cancer cells, which I don't really remember. This is done quite some time ago. So this is just non-irradiated cells. Irradiated cells, these regions are actually accumulation of dead cells. And the investigation of that particular investigation is the control groups. These were groups that were only treated with chemotherapy, cisplatinum. And these groups are both irradiated and chemotherapy. So a combination of treatment with irradiation and cisplatinum provided better effects, and also protons in this case were compared to gamma rays were shown to be better than gamma rays, so which was quite encouraging. The other application that we do of interest to hadron therapy is that we can focus the beam and use individual ions of any kind, of any rate, and by scanning system, we can determine their position at the micrometer scale. Here is just one small example of diamond detector 3D construction, which is basically developed in CERN. And this is the image of the response of this 3D diamond. Red dots means high collection efficiency, blue and green means bad collection efficiency. So this tool is interesting to study the detectors that are being developed and that can be characterized on the microscopic scale. And then, of course, as microdosimeters are microscopic detectors, this is one examples that we did with the University from Rome, Tor Vergata. They constructed different sizes diamond dosimeters based on Schottky diodes, and also with Med Austron, some silicon telescope, which are very small dosimeters of tens of microns. So it is important to image and to measure the response of these dosimeters under the carbon beam environment. And you can see in this top right image that we can even make some damaged areas, so damaged areas, so we can actually study not just response, but also response to radiation. So each of these damaged areas was irradiated a little bit differently, so we can see if the radiation hardness of these devices is proper. We did also some in-air experiments of CMS pixel detectors and some new design detectors, but this I don't have time to go in more details. So what I think is important for this moment is also to say a little bit about sustainability of such a system that we have, because in Southeast Europe nobody gives money to the science, so they give you salaries. 90% of the budget for Croatia, Croatian science is salaries. So only 10% over the salaries, which is extremely small money, is giving to everything else. From that money, basic researchers cannot live, cannot buy even the basic stuff. So this is extremely difficult situation, not just in Croatia, but in many of these Southeast Europe countries. So one has to think about these things when establishing the center of that kind. Another most important is to attract staff. I mean, accelerator like us, we now have 20 people, and this is just impossible without good technicians support, professionals that have to, let's say, for instance, upgrade the computer control of the accelerator. The whole computer control in our accelerator has been built by two persons shown here. And everything, all of these things have to be done with the very low salaries, which is not something one has to mention in this context. So how can you attract such a number of people? Well, by increasing increasing number of projects that can fund incoming and ongoing mobility, by international aspect. You cannot have such a facility with the local users only, and also work with attractive research subjects. And what we did, I think, in the last 20 years, that we could equip our facilities with almost all possible ion beam analysis techniques. So I don't know any other from here that exists that we don't have. And then also we have some unique end stations, for instance, high resolution pixel setup. There are only few, and we use it for calibrate APX spectrometer that is currently on Mars. We have the only one dual microbeam irradiation in the world. We are using dual beam irradiation for fusion research. Only 3 or 4 laboratories in Europe can do that. TOFERDA that I show we use for commercial application and give us some money to pay technicians, for example, because nobody will work for, let's say, 500 euro in an institute when he can get twice more in some private company, and so on. So one has to say also that these capabilities make us good, makes us advantage that we can that we can host users from abroad. So today we have 2 modes, actually 3, Serikeri Consortium and Horizon Project Radia that can find access of foreign scientists to Zagreb. So you can, for instance, see the situation of foreign researchers, visitors in 2007. There are just few during the year. In 2017, we have every second week visitor from abroad. All these blue were paid by some projects. And what happened because of that, the utilization of the beamline raised from, let's say, 700 hours now to 2,500 hours per year. One has to say that at these, well, let's say 20, 30 years ago, we were only funded by the International Atomic Energy Agency, our ministry, and we relied very much on donations. So we have donation of equipment from universities of Uppsala, Rosendorf in Germany, Switzerland, UK, from Oxford, and so on. So these were very important. And then we have also some internal construction of the equipment that has been built, and so this chamber has been built and sold in Bangladesh. And then in the last 10 years, we have now tens of different projects, and this is I'm very proud of that because this is like the 3 or 4 currently working projects. This is Serikeri. Then we have AIDA Innova with CERN. We have DONES preparatory phase. We have Aerofusion. And all these projects contribute somehow to the utilization and to sustainability of the system. And because of that, we will go to the new investment cycle. So we'll get soon the new building for the accelerator where we'll move all the accelerator small and get a new one, and all the beam lines will be transferred to this new site. And hopefully that will be in 2023 finished from now. You can, some of the techniques, if you can note this web page, Atomic Energy Agency site has 4 different demonstrations of ion beam analysis techniques that were filmed in our laboratory. So you can access them at this website. This is under Accelerated Knowledge Portal. These are all about 15 to 20 minutes demonstrations if you are interested in PIX experiment, RBS, nuclear reaction analysis, and microprobe. And now just to conclude, electrostatic accelerators of this kind are excellent instruments for education and training for at the beginning, really, because you have variety of different different instruments for experimental physicists. I think it is extremely valuable. Of course, you still can have many basic research in physics, like interaction with materials, which is completely unexplored area. Well, just to tell you one fact that with the accelerator of this kind, you can inject any atom to any microscopic position in any other material. So you can force to create materials which cannot exist in nature. For example, to create color centers for quantum center or quantum computer, quantum sensing. This is one of this way. Then, of course, applied research in many interdisciplinary areas. And as I mentioned briefly, we also have some commercial applications like for analysis. So I think that I'm done with this. And this is just one picture of the spark of the electrostatic accelerator from the inside, which is quite pretty nice. And of course, it is unwanted event. We don't like sparks. In this case, we were using sparks to test the electronics, which is inside of the inside the high voltage terminal. So I wish you thank you, and I can accept the questions. Thank you.
Okay. Right, Milko, I leave them in your hands.
Okay, so comparing with synchrotron analysis, which aspect of the ion beam analysis is better? Well, synchrotrons have advantage. They are more accessible because they have many beam lines at one time. X-ray absorption spectroscopy and synchrotron is better because they can give you information about the chemical composition. X-ray PIXE can give you only elemental composition. Radiation concerning X-ray spectrometry is better for some elements. Synchrotron has to be adjusted. So adjusted by means of adjusting the energy of X-rays for the analyte elements. But ion beam analysis have not just X-rays, but we have also, like what I mentioned, MEV SIMS. So we have mass spectrometry, which a synchrotron cannot do. So we can analyze masses of the molecules. So there are some advantages. Did you experience a lot of X-ray emission along the accelerator tube? Well, the first set of tubes we had long time ago were classical accelerator tubes, and they had extremely high radiation of the X-rays because of the electron accelerator. But 20 years ago, we acquired so-called inclined field tubes, which prevent electrons of traveling. They are bended, and they are not accelerated, and no gamma ray X-ray emission exists. So we actually can walk by the accelerator, and it is extremely good that you don't need to have much radiation protection in some of the cases. Not permanent. Well, hadron therapy, as far as I know, I mean, look, the hadron therapy centers are 200 million euros funding. The access to is very difficult, and you have hundreds or thousands of patients which can be treated equivalently well with the conventional techniques. I think that the hadron therapy has a future for very difficult cases, for cases that no other technique can be used. So, well, yeah, there is maybe one more question. Yeah, diamond. I guess yes. Diamond detectors are extremely perspective, in my opinion, detectors, because diamond is a unique material. So imagine you can produce diamond membrane of only 1 or 2 microns thick. So it can serve as a window towards the cells. It is a biocompatible material, so you can even grow cells on the material, on diamond. And in the same way, you can detect ions passing through it. So this is extremely useful technology. Diamonds are still expensive, but they are going down with prices. And well, okay, does it perturb the beam? As if you remember the trajectory, if the trajectory of the beam through material when they are still high energy is not perturbed, so trajectory is remain the same, at least when we have very thin thin material like this. So it doesn't make big perturbation. Yeah. Okay.
All right.
Yeah.
Milko, thank you so much for your lovely presentation and also for answering these questions. We now have a coffee break. We will be back at 11 for another 2 talks